So far you have learnt about the CMC, the factors that control the shape, size and CMC of micelles, and you have learnt about this how CMC decreases strongly with increasing alkyl chain length, and notice how the addition of electrolyte to the solution of ionic surfactant decreases the CMC and increases the micellar size. Now in this module you shall be able to know about the important phenomena of solubilization and its relation with micellization. You will also know about the various factors affecting the solubilization capacity and site of solubilization. You will also learn about the thermodynamic role of molar solubilization capacity and the micelle water partition coefficient. It has long been known that the aqueous solubility of sparingly soluble or insoluble substance can be increased by adding an appropriate third component. Systematic studies using surfactants led to this phenomenon being called solubilization. It plays a very important role in industrial and biological processes. For example, the dissolution of drugs into aqueous solution and their transport through the body, the preparation of agriculture chemical solutions, and the recovery of oil depend on solubilization by suitable surfactants. The importance of solubilization is likely to be very important in the future. This module focuses on the study of solubilizates in micellar solution. Solubilization is defined as a particular mode of bringing into solution substances that are otherwise insoluble in a given medium involving the previous presence of colloidal solutions whose particles take up and incorporate within or upon themselves the otherwise insoluble material. This definition is too narrow because the increased insolubility is not always caused by direct introduction of colloidal particles into the system, but more often it is due to the presence of third component. Therefore, the broad definition is the preparation of thermodynamically stable isotropic solution of a substance normally insoluble or very slightly soluble in a given solvent by the introduction of additional amphiphilic component or components. Now let us see about solubilization. An important property of micelles that is particularly significant in pharmacy is their ability to increase the solubility of sparingly soluble substances in water. In this context, solubilization can be defined as the spontaneous dissolving of a substance by reversible interaction with the micelles of a surfactant in water to form a thermodynamically stable isotropic solution with reduced thermodynamic activity of the solubilized material. If we plot the solubility of a poorly soluble compound as a function of the concentration of surfactant, usually the solubility is very low until the surfactant concentration reaches the CMC. At surfactant concentration above the CMC, the solubility increases linearly with the concentration of surfactant, indicating that solubilization is related to micellization. You can see from this diagram the concentration of a poorly soluble compound as a function of the surfactant concentration in aqueous solution.
Now let us try to understand the solubilization, how that at CMC, if we try to plot the solubility of a poorly soluble compound and this was as a function of concentration of surfactant, then usually the solubility is very low until the surfactant concentration reaches the CMC value. So let us consider this plot, and you can see here that in this axis, the y-axis, it is the concentration of the poorly soluble compound in solution which has been taken, and this is being plotted with the surfactant concentration. So you can see from this graph that the graph is moving this way. That is, as the concentration of the poorly soluble compound in solution increases, the surfactant concentration increases, but that happens only after a point when it reaches the CMC value. And CMC, you know, it is the critical missile concentration. So what we can say is that below the CMC, then there is no solubilization which happens. So there is no solubility when you have the concentration in this value. On the other hand, if you look at all these values in this area, that is either it is at this point or this point or this point or this, then at the surfactant concentrations, which is, you can see the values here, at the surfactant concentration which are above the CMC value, in this case the CMC value is here, then the solubility increases linearly. So you can see there is a linear plot here with the concentration of the surfactant, and this indicates that the solubilization is related to the missile formation, that is to the missilization. And at the CMC, when the missile formation takes place, then the solubility keeps on increasing as the concentration of the poorly soluble compound is increasing along with the surfactant concentration.
We can see this from the representation of sites of solubilization depending on the hydrophobicity of the solubilizate. Non-polar solubilizates like aliphatic hydrocarbons are dissolved in the hydrocarbon core of ionic and non-ionic micelles shown in position 1. Water insoluble compounds containing polar groups are oriented with the polar group at the core surface interface of the micelle and the hydrophobic group buried inside the hydrocarbon core of the micelle shown by position 2 and 3. In addition to these sites, solubilization in non-ionic polyoxyethylated surfactants can also occur in the polyoxyethylene shell, that is the palisade layer which surrounds the core, shown by position 4.
Let us try to understand the micellar solubilization, which is a powerful alternative for dissolving the hydrophobic drugs, and how it happens. As you know, hydrophobic drugs, these are not water loving, rather water repelling, that is, they are water insoluble. And obviously, if drugs or the medicine, they have to function in the body, they have to become solubilized. So let us understand how it happens. You already know that in the micelles, let me make a micelle here. So these are the ionic part, and these are hydrophilic, that is water loving. But when you see the inner part of the missile, which is referred to as the core, then there is more of this organic and the hydrophobic part. And as we know, like dissolves like, so if you have the hydrophobic drugs, obviously the more hydrophobic nature, more they will be seated inside the missile, that is inside the core. So let us try to understand and see how the different positioning of the drugs can be there in this missile. Now here you can see shown is the missile, and this is the core of the missile where it is predominantly hydrophobic in nature. So when you have the drugs which are highly insoluble, that is they are hydrophobic, then they will be positioned at this position, that is inside the core. You can notice that this part, that is the outside part, the periphery of this missile, is hydrophilic, and all these water soluble drugs will be positioned anywhere in this area, as it's shown by position 4. You can see one of the drug being shown here. Now if we talk about the drugs which have intermediate solubilities, what do we mean by that? That is, there will be drugs where there will be some hydrophobic part and some hydrophilic part. So they will be partially soluble in water. Now in these cases, what happens is these drugs will be positioned at these. That is, they will be in between the core as well as the outside. That is, the core, you know, it is hydrophobic and this is hydrophilic, so they will be positioned in between these two. So what we can sum up is that the spatial position of the solubilized drug in a missile, it will depend upon the polarity. So you can say the non-polar molecules will be solubilized in the micellar core. So non-polar go there, that is inside the missile core, and the polar molecules or the polar drugs will be there, which will be either at the intermediate position or they will be distributed along the surface of the missile.
Mentioned earlier, the solubility stays very low until the CMC is reached, while above the CMC it increases rapidly and almost linearly with the surfactant concentration. This is shown in this figure where we have used the 4 surfactants and we have seen the solubilization of dye increases linearly after the CMC values. Let us see some factors affecting solubilization capacity. Nature of surfactant and solubilization. When the solubilizate is located within the core or deep within the micelle structure, the solubilization capacity increases with increase in alkyl chain length up to number of carbon atom 16. Further increase has little effect on solubilization capacity. The effect of an increase in ethylene oxide chain length of a polyethylated non-ionic surfactant on its solubilizing capacity is dependent on the location of solubilizate within the micelle and is complicated by corresponding change in the micellar size. The aggregation number decreases with increase in the hydrophobic chain length, so there are more micelles in a given concentration of surfactant, and although the number of molecules solubilized per micelle decreases, the total amount solubilized per mole of surfactant may actually increase. For a simple homologous series of solubilizate, a decrease in solubilization occurs when the alkyl chain length is increased. Now let us see the temperature effect on solubilization. For most of the system, the amount of solubilized increase as temperature increases. This increase is particularly pronounced with some non-ionic surfactants where it is a consequence of an increase in the micellar size as the temperature increases. In some cases, although the amount of drug that can be taken up by a surfactant solution increases with temperature increase, this may simply reflect an increase in the amount of drug dissolved in the aqueous phase rather than an increased solubilization by the micelle.
Let us now try to understand the binary phase diagram, this between the surfactant water. So you can see here this binary phase diagram. The concentration is plotted with the temperature. Now this is the solubility curve. Furthermore, you can see that this is the CMC curve. And below this there will be monomers which will exist in water, and above this CMC curve you can see there will be micelle formation. So what we can interpret from this plot is that the solubility of surfactants is highly temperature dependent, and this is clear from this sharp rise. You can see that as the temperature is increasing, the solubility initially is low here at low temperature, but as the temperature increases, that is in this range, you can see there is a steep rise in this solubility curve. So the solubility increases very rapidly, and that is happening in a very narrow range. You can see that the solubility is increasing. Another thing to notice is that there is no micelle possible above a certain temperature. That is, when you go into very high temperature range, then there will not be any micelle formation. And another thing that you can notice is that if you look at this point, that is, if we look at this point, then this is the point where you can see that this solubility curve is meeting the CMC curve. So this point where the solubility curve meets the CMC curve is the Kraft point, and this defines the Kraft. Another thing you can say is from this plot is that this point, that is the Kraft point, and corresponding to this temperature, which is referred to as Kraft temperature, This Kraft temperature can be regarded as the melting point of this binary phase diagram, which is between the surfactant and water. And due to this, you can see that this is the place that is below this temperature, which is the Kraft temperature. Then they will be existing as hydrated crystals, and then beyond this, that will go into solubilization through the micelle formation. But micelle formation is also not beyond a particular temperature, so that you can see from here, that is, the solubility will take a steep rise when the temperature increases.
Now let us see the thermodynamics of solubilization. From the thermodynamic point of view, the solubilization can be considered as a normal partitioning of the drug between two phases, micelle and aqueous, and the standard free energy of solubilization, that is delta Gs naught, can be represented using expression which is delta Gs naught is equals to minus RT ln P, where R is the gas constant, T is the absolute temperature, and P is the partition coefficient between the micelle and the aqueous phase. The solubilization of a molecule by a surfactant can be evaluated on the basis of two descriptors. They are the molar solubilization capacity X and the micelle water partition coefficient P. X is defined as the number of moles of solute that can be solubilized by 1 mole of micellar surfactant and characterizes the ability of the surfactant to solubilize the drug. It can be calculated based on the journal equation for micellar solubilization, that is X is equals to S total minus SW divided by C surfactant minus CMC, where S total is the total drug solubility in surfactant solution, while SW stands for the solubility of the drug in water. C surfactant is the molar concentration of surfactant in solution, and CMC is the critical micelle concentration. The term C surfactant minus CMC is approximately equal to the surfactant concentration in the micellar form, and therefore X is equal to the ratio of drug concentration in the micelles to the surfactant concentration in the micellar form. On the other hand, the micelle water partition coefficient is the ratio of drug concentration in the micelle to the drug concentration in water for a particular surfactant concentration, as shown by this expression. P is equals to S total minus SW divided by SW. Combining these two equations, we can relate the two solubility descriptors, according to which for a given surfactant concentration, P is equals to X into the difference of C surfactant and CMC divided by SW. It can be seen that P is related to the water solubility of the compound, in contrary to X. In order to eliminate the dependence of P on the surfactant concentration, a molar micelle water partition coefficient, that is Pm, corresponding to the partition coefficient when the concentration of surfactant is equal to 1 molar, can be defined. Pm is equals to X 1 minus CMC divided by SW. The lower the CMC value of a given surfactant, the more stable are the micelles. This is especially important from the pharmacological point of view, since upon dilution with a large volume of the blood, considering intravenous administration, only micelles of surfactant with low CMC value still exist, while micelles from surfactants with high CMC values may dissociate into monomers and their content may precipitate in the blood. Now we see the location of solubilizate in micelle. The position of solubilizates in micelles as well as in living membranes provides very important information concerning the physicochemical properties and physiological functions of both solubilizate and micelle or membrane. This property can be investigated using probe molecules. The spectrum of the probe molecule indicate the surrounding conditions. The absorption spectrum of a molecule depends on the dielectric constant of the medium surrounding the molecule. The dielectric constant of a micelle ranges from 2 for the liquid hydrocarbon in the inner core to 80 for the water of the outer micelle surface. These are generally accepted rules for solubilizate position which are derived from many works. 1. Non-polar aliphatic hydrocarbons locate in an inner hydrophobic micellar core. 2. Semipolar and polar compounds such as alcohols, acids and amines locate at the so-called palisade layer of the micelle, with the polar group at the micellar surface and the non-polar hydrocarbon group in the micellar core. Third, aromatic hydrocarbons such as benzene, toluene and naphthalene sit in the micellar core and at the micellar surface. The fraction of solubilizate occupying each of these two sites depend on its concentration in the intermicellar bulk phase. The fraction in the inner core increases with increasing concentration in the bulk phase because the increase in the chemical potential of the solubilizate enable it to move towards the micelle core. There are a number of possible loci of solubilization for a drug in a micelle, which can be seen from this diagram. The diagram 1 shows the hydrophilic drug can be adsorbed on the surface of the micelle. The diagram 2 shows the drug with intermediate solubility should be located in intermediate position within the micelle, such as between the hydrophilic head groups of PEO micelle and in the palisade layer between the hydrophilic group, and the diagram 3 shows that drug reside at the first few carbon atoms of the hydrophobic group, that is in the outer core. Diagram 4 shows the completely insoluble hydrophobic drug may be located in the inner core of the micelle. The existence of different sites of solubilization in the micelle results from the fact that the physical properties such as microviscosity, polarity and degree of hydration are not uniform along the micelle. Now let us see some pharmaceutical application of solubilization. The solubilization of phenolic compound such as cresol, chlorocresol, chloroxylenol and thymol in soap to form clear solution for use in disinfectant. Solubilized solution of iodine in non-ionic surfactant micelles for use in instrument sterilization. The solubilization of drugs, for example, steroids and water-insoluble vitamins and essential oils can be done in non-ionic surfactants, usually polysorbates or polyoxyethylene sorbitan ester of fatty acids. Now let us summarize what we have learned. From this module, we have come across an important property of micelles, that is solubilization. It is the spontaneous dissolving of a substance by reversible interaction with the micelles of a surfactant in water to form a thermodynamically stable isotropic solution with reduced thermodynamic activity of the solubilized material. There are various sites of solubilization within the micelle that varies depending upon the chemical nature of solubilizate. Solubilization capacity gets affected by three factors, namely nature of surfactant, nature of solubilizate, and temperature. The solubilization of a molecule by surfactant is defined by two factors, 1. Molar solubilization capacity and 2. Micelle water partition coefficient. The micelle with lower CMC values are found to be more stable and can act as good solubilizer, which may not get dissociated in large volume of solvent. Position of solubilizate in the micelle generally depends on its nature, as nonpolar aliphatic hydrocarbons locate in an inner hydrophobic micellar core. Semipolar and polar compounds locate at the palisade layer of the micelle, with the polar group at the micellar surface and the nonpolar hydrocarbon group in the micellar core. Aromatic hydrocarbon lie in the micellar core and at the micellar surface.